So, good evening, everyone. I'm Anish Ambikar, PMRF and PhD candidate from Aerospace Engineering, ISC Bengaluru, and welcome to this week's live session for the NPTEL course, Computational Mathematics with SageMath. Uh, as is the custom every week, we'll be going through a set of different problems which will cover the basis and the concepts that have been taught in that particular week's lectures. So we'll go through the first problem and then I'll just show how I've done this in the SageCell web page as well. So the first problem, it asks us to find the quadratic which fits the set of points given below. So the data of points is given here. X coordinate varying from 0 to 9 in steps of 1, and then your y coordinate going from -5 to +125. If I plot the points, to do so, I'll be using the points function. We have already seen this, that this points function takes a data which contains x comma y coordinates in a nested array. So if I just do points and show how the points look like, I see a distribution of the data points like this, and to find the quadratic equation which best fits this provided data points, we'll be making use of two different methods. The first is the find fit function, which is an inbuilt function. If you look at the help on this, so we are told that it takes like two arguments, unnecessary arguments. First is the data, which is a 2D array, x x1 x1 y1 x2 y2 and so on. And the next thing is model. So model is an expression or a function. So far all the functions that we have been defining, if you remember, they are essentially expressions. So if you define a function that can be along with the data that can be fed into this find fit function. So what we are doing here is we are initializing variables a, b, c and t, and I'm writing model of of the variable t as at square plus bt plus c. So this is my model form, which is a quadratic function in the variable t, where a, b and c are my parameters. After this, I'll be running the find fit function using all the data points that we have above along with this model form, and asking it to return solution in the form of a dictionary. Finally, I'll be also asking it to substitute the fitting parameters inside the model itself and then show what we get. So if I run this, as you can, it's still running. So it's showing us the model. So model is provided the variable t. We get at square plus bt plus c, and the find fit basically shows me that my fitted parameters are a is 1.85, b is minus 1.75, and c is minus 6.39. Right. So this gives me my fitting parameters, and when I plot for both the fitted models and the points, what do I see? I see a curve that looks like this. Right. Uh, okay, so the same process I will quickly show in the Sage Cell server. I have already written this, but in the Sage Cell server, I am basically putting uh, all the four different cells that I have written in my Jupyter notebook. So, which is my data, my plotting points, my inbuilt function, as well as my fitted model endpoints. So, I've just pasted all those four cells here directly. And if I run evaluate, language has to be set to Sage. If I run evaluate, this is what I see. So this is my first graph of points, my function, my fitted parameters, and my fitted function with data points. So this could be a workaround if you if you are unable to install, say, a higher version of Sage, such as 10.1 or 10.2. The same, if we again want to fit our data points to this at square plus bt plus c sort of quadratic function, another approach could be by minimizing the error. So how do we do that? We define our three parameters a, b, and c. Then we write down our error in the form of y of I minus my function of x of I. So my y of I is data I1, and my function of xi is basically a into data I0 square plus b into data I0 plus c. So I'm basically doing, sorry, I'm basically calculating error for each of the data points, and once that is done, what I'm doing is I'm writing a different larger function. So I should do like this, show error, right? So what I'm doing is I'm writing a different larger function f of abc, which sums all the errors for all the data points. So we have 10 data points, all of whose error value, which is the difference between prediction and output, square of that is summed to obtain this large function. So ABC going to like all this bracket. Now what do we do is to minimize the error, we basically have to minimize this function f of ABC, and to do that we have already seen in the previous weeks that we calculate the partial derivative of f with respect to a, b, and c, and set them to 0, and then find the values corresponding to a, b, c, which are our variables. So if I run this cell, what do I get? I get my a, b, and c values to be like this, and if I have to say check how they compare, I can do S0 A, so S0 A dot N as my value of A. So you can see that from this minimization of error approach, we are getting A to be 1.85, so which is exactly same as what we got from our model fit function. You can also check for B and C, they're around the same values. Okay. Uh, so if I by plotting it, I can also, by plotting I can also like verify to be the same. So yeah, so this solves the first problem for best fitting a quadratic equation to a set of data points. Next, we have another example where we are trying to find the best fit for a line y is equal to ax plus b to a set of points. Again, we have been provided with points data from, so like again you have 10 points, x going from 1 to 10, and different values of y. If I plot only the points, I see something like this. So there's a bit of zigzag, but it seems like roughly we can estimate a trend line, a straight trend line going down like this as x increases. So if I now look at, say, what the solution looks like using the inbuilt function, for that I'll be again doing the same process. I'll be specifying my variables m, c, and t, and then I'll be defining my model of t as m into t plus c, which is basically an equation of a straight line. Next, I fit the model using find fit function. We have seen above that it takes data input, so an array of xy, and the model input, which is an expression which you already have here. And once I run this, I get uh, I get two values of I get the optimal value for C and M. So intercept and slope are 4 and minus 3.03 respectively. Next, I want to plot the fitted model. So what I do here is I again assign this M and C are no longer variables in or like symbolic variables like defined above. They become constants and their values come from this fit of M and fit of C. We plot points. We plot M into T plus C, where T goes through a different range. And with this in mind, if I run this function, this is what I obtain. So it seems like our data points do follow a linear trend line, which is given as the form of y is equal to minus 3.03x plus 4. Same thing as we have seen earlier, we can use a minimization of error approach to do that. Again, same thing, again the same process, define variables, write down the error between each predict between write down the error for each data point defined as the difference between model prediction, which is mx plus c, and my actual value, and then write down my big error function as sum of square of error for each data point. So this is how it looks like. Next, we calculate, since we want to minimize this large error function, we calculate the partial derivatives of the large error function with respect to the two variables involved, which are m and c, and then solve for the partial derivatives going to 0. Once this is done, I essentially go the plotting route again, where I plot for the trend line that I am obtaining from my fitted, sorry, from my partial, from my minimization solution and the point. So again, we arrive at the same point. You can also compare that my C and M values are same as what we obtain above. Okay, so in both of the above two examples, we covered how do we basically do fitting for our given data points and the choice of model function. Are there any doubts here in either of these two? If so, you could ask them. I believe then this is quite clear. The next problem that we have is to find the minimum and maximum for a function f of xyz defined as xy plus yz on the unit sphere x square plus y square plus z square equal to 1. This is basically an example of constrained optimization. So minimum maximum of f of xy given some constraint g of xyz. The process again starts similar, where we first define our symbolic variables x, y, z and lambda, written here for short. We define our functions f of xyz and g of xyz. So these are our function definition. Next, to minimize or maximize f of x, a function f with the constraint provided by function g, we basically write down the composite function f of xyz plus or minus lambda of g of xyz, and because g of xyz is essentially 0 in the case of an equality, we can move around this one to the LHS and make this equality as 0. Once we take partial derivative of the composite expression, we arrive at solutions for f of xy, for solutions for the extremum of function f with the constraint g. So the way we execute this in here in SageMath is for the functions f we calculate the partial derivative with respect to x, y, and z. For the function g again we do the same thing. So I just can already like guess what this partial derivatives will be, right? So for the first case, there, so dou f by dou x is basically y, dou f by dou y is z, and dou f by dou y is x plus z, and dou f by dou z is y. Similarly, 2x, 2y, and 2z are the dou g by dou x, dou g by dou y, and dou g by dou z respectively. To evaluate the minima maxima, we basically can solve the equations. F of x is equal to lambda of dou f by dou x equaling lambda of dou g by dou x, dou f by dou y equaling lambda of dou g by dou y, and dou f by dou z equaling lambda of dou g by dou z, along with g going to 0 separately. Once we solve these from these four equations, we wish to obtain our four variables, which are x, y, z, and lambda, and we are asking Sage to return the solution in the form of dictionary. So you can see that Sage gives us like six solutions in total. How do we calculate? How do we find out which of these are minima maxima? We basically a crude way to do so could be running a for loop, calculating the function value f of xyz at each of these xyz values. So from this you can see that the in the six for the 6 points function value that we are obtaining is between 1 by square root of 2 and minus 1 by square root of 2. So the minima would be at these points, which is x is equal to 0.5, y is equal to minus 1 by root 2, and z is equal again equaling half. So you have got two minima and two maxima coming out here from this constraint optimization problem. Next, again, we have a similar problem where we want to find again constraint optimization for the function f of xy equaling xy cube subjected to 2x plus 3y equaling 4. So same steps. Start by defining symbolic variables x, y, lambda. Define your function expressions f of xy and g of xy. Next, to estimate where those minima or maxima could lie, what we are doing is we are basically plotting a contour plot for the function f of xy between with x and y both bounded randomly between -5 to 5, and I'm also asking it to print labels so that we get an estimate of how f of xy looks like. Say along with that, on the same contour, what I'm doing is I'm plotting the function y is equal to 4 minus 2x by 3. So this is the other way around. Yeah, 4 minus 2x by 3. So I'm just playing around with g of xy to obtain y as a function of x, and for the same range of x. And now I'm plotting both. So what do I get? I get a function, I get a line like this. So on this line, we wish to find out where the function is minimum or maximum. You can see that for the for the first and the third quadrant, it seems like the function value is increasing away from the origin. So it's going from 50, 100, 150 all the way till 450. So there is no decreasing trend here. Similarly, on this other on the other two quadrants, the values are like increasing in magnitude, but in the have a negative sign. So the values are only zero at x and y being x or y being zero. So that is again could be obviously inferred from the equation itself. Okay. Next, to solve this constraint optimization problem, again we calculate the partial derivatives of f and g, dou f by dou x, dou f by dou y, dou g by dou x, and dou g by dou y respectively. And the process is same. We write down the composite equation h is equal to f plus lambda g, and then we try to calculate the extremum of h by taking partial derivative with respect to x and with respect to y, as well as setting g equal to 0 as our constraint equation. With this in mind, I calculate the solution function. So I get two different solution values. First is, I'll print for both of these. So for both of these values, x comma y, you can see that what f of xy looks like. It seems like we have a minimum at x minimum when y equals 0. If I for which x would automatically become 2. If I now plot, say, do a 3D plot for the function f of xy, z equal to f of xy, this is how it looks like. So the first and the third quadrants increase very rapidly, whereas the second and the fourth quadrant decrease very rapidly. Somewhere here in between we have our constraint line. So one way along the constraint line, our uh, so on both ends of our constraint line, our function basically increases to a point, then decreases and goes negative. So somewhere here in between we have a maximum, and here we have uh, two values. So from this point, so like x is equal to 0.5 and y equal to 1, this seems like the point which has maximum value xy cube subjected to the constraint equation of the line 2x plus 3y equals 4. Okay, right. So this is the maxima that we get. We cannot comment on minima because minima will just keep on becoming negative. So right. So this solves this problem. A similar example on constraint optimization. Again, we wish to uh, figure out the minima and maxima for the function given by x square minus 2x plus y square minus z square plus 4z, subject to this equation. Sorry, subject to this constraint x minus y plus 2z equals 2. Again, the same steps. Define symbolic variable. Define your expressions f of xyz, g of xyz. Next, define your composite equation. So that is basically h is equal to f plus or minus lambda g. In this case, since we are equaling lambda g, our composite function would essentially be h is equal to f minus lambda g. Right. So this is the composite function that we are uh, extremizing. To do so, we calculate the partial derivatives of f and g respectively, or we could have directly done for h and set those partial derivatives with respect to x, with respect to y, and with respect to z to 0, as well as providing the condition for the constraint to be 0. So we solve these four equations using the solve module and try to calculate the values of x, y, z, and lambda in the form of a solution dictionary. So we only get one value here, and if I print this is what it looks like. So how do we know whether this is minima maxima? We could say calculate at any different point. So say h of, so I could say give any other point. So 1, 1, 1, and ask it to calculate the function at the same point. Play around with the values a bit. You can see. Oh, sorry. Oh, no, wait. I made a mistake here. X minus y plus 2z is 2. So I need z is it. X1 is say 1, x1, y1 equaling 1, 1, z1 equaling 2 plus y1 minus x1 into zero point 0.5. So this is my constraint equation. And then at this point we want to print our solution. So you have x1, y1, z1, and now that is being fed to my function. And so if I say do 5, if I do minus 10, minus 100, so this is what we see. So it seems from this we can infer that the extremum point that we have calculated is minima for this function subjected to this constraint plane. Okay, so the above three problems basically are different examples of solving constraint optimization problems. If you have any doubt on any of these, you can ask them now. Okay, then we'll go with the next one. Suppose, so the next set of problems is on vectors in SageMath. So here in this example, we are asked to take any three vectors A, B, and C in R cube and verify the following statements. So the first one is on cross product. A cross B cross C is A dot C into B minus A dot B into C. And the second one is on a combination of dot product and cross product. So A dot B cross C, so B dot C cross A is C dot A cross B. So like a cyclic order here. The second one is also used in calculating, say, the volume of a parallelepiped, but I think we will be looking at that later. So suppose we take the three vectors, A is 1, 0, 0, B is 1, 1, 0, and C is 1, 1, 1. If I do if I now do a vector plot for the vectors A, B, and C, A is in red, B is in green, and C is in blue. So it looks like. So A is 100, B is 110, and C is 111. Right. Now I wish to calculate, I wish to evaluate or rather check the first identity. So for the first identity, you have A cross B cross C. So B cross C is written as B dot, we are writing it like B dot cross product C, and then A cross product B cross product C. So this becomes my LHS of the first identity. My RHS is nothing but A dot C written as A dot dot product C into vector B. So this is a scalar, we are multiplying with the vector B. So uh, each component of the vector will get scaled. If this was a vector and we were doing a direct multiplication, then it could be term-wise multiplication. So you have to be careful using this. But because it's a scalar, I'm using it like this. So A dot C into B minus A dot B into C. So that becomes my RHS of the first identity. And then I just do a print statement comparing LHS and RHS. So we can see that indeed LHS and RHS are both same and both are the vectors 0, 0, minus 1. Okay. The next identity that we have is A into dot product B cross C. So you have three terms there, an LHS, middle term, and then RHS. So A dot B cross C, B dot C cross A, and C dot A cross B. So all three terms are here. And now we want to print what the second identity looks like. So the value that we end up is essentially one, scalar one. Okay, pretty straightforward. Next example that we have is again on some identities. Suppose we have two 3D vectors, u is equal to 3 minus 2 4 and v is equal to minus 2 5 3. Now we are asked to calculate the orthogonal projector p of the vector v onto vector u, and we are asked to also show that the vector v minus p is orthogonal to u. So we begin by defining vectors u and v as 3 minus 2 4 and minus 2 5 3. Next we do a vector plot. U is blue whereas v is green in color. So this is how you can see it. Now we want to see the projection of vector v, so which is green, along vector u, so which is blue. You can see that from an eye test, it seems like the angle between these two is might be greater than 90 degrees, which means the projection of v might come on the opposite side of vector u. But we'll calculate that. So projection of vector v is basically v dot u divided v dot u multiplied by a unit vector which is along the vector u. So sorry. So how do we write the unit vector along vector u? It's nothing but u divided by norm of, sorry. So the unit vector is nothing but u vector u divided by the L2 norm of vector u. So which is this, and I'm again multiplying v with unit vector u, v dot dot product unit vector u, and if I do uh, projection. This is how it looks like. Okay, we have, sorry. Yeah. Okay. Sorry. We are also calculating the perpendicular vector, which is basically v minus, uh, projection of minus the projection vector p. So this is what we get it to be. If I now plot all the vectors, so my projection is yellow. To play around a bit. So this is how it looks like. My green is my v vector, and green is my v vector, blue is my u vector, and this is how the projection of v along u looks like. The difference between this is basically basically normal to vector u. So to show that, we also have to do p perpendicular. So p perpendicular dot product u. I think this I have made a mistake here itself. So the projection is smaller than I had thought. I had made a mistake here. So it should be v into dot product of v with respect to unit vector along u, and then multiply the whole. This basically gives you the scalar or magnitude, and then multiply this magnitude with the unit vector along u. So it is u by norm of u. Once you do this, we basically get our p perpendicular or v minus p to be perpendicular to u. So the dot product vanishes. The second identity that we had to check was along norm of u plus v whole square plus norm of u minus v whole square equal to twice of norm of u square plus norm of v square. If I go here, what do I see is LHS is norm of u plus v whole square plus norm of u minus v whole square, and RHS is twice of norm of u square plus norm of v square. If I do run this print statement, I get LHS and RHS both equaling 134. Okay, so yeah, so this is what we get here. The next example that we have is on finding the volume of a parallelepiped generated by three vectors u, v, and w, which are given as here. So 3 minus 2 4 minus 2 5 3 and minus 3 minus 2 4. These are my three vectors. If I do show, next I am defining a function called as plot parallelepiped for three with three input vectors A, B, and C. First, I'm creating a plot object for the three vectors A, B, and C in three different colors, red, green, and blue. Next, I'm adding different lines or different edges of the parallelepiped. All of them are colored black, and you can see that like it's basically a line that goes from say A to B, B similarly from B to A plus B, A to A plus C, and so on. So all these are like the 8 different edges that you can construct. You can also verify them yourselves. And from this, I'm basically in the return part, I'm asking it to show this entire plot object P. Right. If I run this for our function, what do I get? I get a big looking cube like this. So this is my U, V is green, and W is blue. And then this is how the parallelepiped ends up looking. Right. So if I want to calculate the volume of this parallelepiped, we know the formula is basically U dot V cross W, or like a cyclic combination of the three. Run this print statement, the volume that is bounded comes out to be 156. So this is what we obtain from this. So this is how we solve this particular question. Next we have been asked to create a user-defined function to evaluate angle between two given vectors. The function that we are defining is I have given it a name called as getAngle, and the logic that we are using is the angle between two uh, two projections. If it is theta, then I get cos of theta to be basically A dot B upon norm of A into norm of B. So it's a very standard elementary uh, formula that I think we all know. And once I calculate cos of theta, what I'm doing is I'm calculating uh, r cos of whatever cos value we obtain and asking it to be returned in the numerical form. So suppose I run it on the vectors AB, we have already defined them to be 100 and 110. We expect the angle to be pi by 4, 45 degrees, and that is essentially what we are getting, 0.785 in radians. If I have to convert this to uh, degrees, that would be nothing but 180 by pi. This whole thing returned as numerical value. This is what we get. So we get 45 degrees. If I have to check the angle between U and V, this is how they are defined. The angle turns out to be 96 degrees. Okay. Because of our cos, we basically will get the angle between, for any cos of theta, we'll get the angle between 0 and 180 degrees, which should give us the smaller of the two angles that we get between, and the other one being basically 360 or 2 pi minus whatever theta we get here. Okay. So far, if you like, I think questions are straightforward only. But if you have any doubt, you may ask them now. Okay, we move on to the next example where we are asked to calculate the area of a triangle with vertices as vectors. So here we have been given vertices as 1, 1, 3, B being 2, minus 3, 4, and C being 3, 1, minus 2. To address this, we define a function called as plot triangle, which first plots the 3 points as vectors A, B, and C respectively in 3 different colors, red, green, and blue. Sides of the triangle are basically uh, the difference between the 3 vectors. So B minus A, C minus B, and A minus C respectively, which is why they are being plotted as a 3D line between 2 points A to B, B to C, and C to A, all colored black. And then we are returning this plot object P, basically showing this plot object P in the provided frame. So how do we execute this? We define our vectors 1, 1, 3, 2, minus 3, 4, and 3, 1, minus 2. We use the plot triangle function. So this is how it looks like. My red, green, and blue basically create points A, B, and C respectively, and the triangle is at an angle, so it's oblique. This is my triangle. If I remove the frame, what do I see? Without the frame, this is what I see. This is my triangle ABC. To calculate its area, we'll be using the formula where we basically calculate the cross product between two adjacent sides of this triangle. That gives us the area of a parallelogram, and we then divide it by half to obtain the area of this triangle. So to do that, we are defining side AB as A minus B and side BC as C minus B. So side AB, side BC, and then basically taking cross product of this vector with this vector, dividing it by half, and calculating its absolute value gives me area of the triangle. So the area of this triangle is 11.324. Okay, so this covers the set of problems that we had for on the topic of vectors that we learned in previous class. I presume since there are no questions being asked, I presume that this is all clear. If not, I'll wait a moment. If you have any questions so far, you may ask them now. Okay. Next, in the next half of the week, we learn basically about how to solve system of equations, different uh, different vector spaces that exist, and some concepts related to that, including basis, linear independence, and so on. The first example that we have on that is on solving a system of equations using row reduced echelon form, RREF. So the system of equation I've already written in matrix form is basically 2a plus b plus c plus 8d equaling 24, and similarly you can look at the other 3 equations from this. Moving forward, we'll be defining first the matrix A, which contains all my coefficients in the correct order, and matrix B, which contains my column vector on the right hand side. again everything in the correct order. From this, I define my augmented matrix A augment B, which looks like this. So, right. And next, what I do is basically run the uh, row reduced echelon form. Before that, we'll quickly look through the help. So it only it basically consider basically it will calculate the row reduced echelon form for whatever matrix we are feeding it. So integer dense matrix integer dense. If I do augment dot row reduced echelon form, this is what I obtain. Right. So this basically is directly gives me the solution for the variables a, b, c, and d respectively are minus 67 by 7, 701 by 161, 1773 by 1661, and d being 559 by 161. This is what I get. If I want to check this, I could say define. I could so to be and define it to be 67 by 7, 701 by 161, 1773 by 161, and 559 by 161. Then I do have to put a vector here. So, so this is what I get Ax. This is indeed equal to B that we have seen. Right. So row reduced echelon form basically gets us the answer very quickly. We have seen this in class also how logic works, that in the augmented matrix we multiply basically we can add a different row or add entries of another row or multiply or create a linear combination of two rows and just plug it in. So we do it step by step till we get a pivot, scale down the pivots to be one each, and then remove the upper triangular values if there are any to obtain the diagonal matrix from row reduced echelon. Next, we are asked to solve a system of equation. So here we only have here we only have here here we have four equations written in three variables. So sorry. Okay. In this example, we have been asked to calculate solution for systems of equation. So we have three equations in four variables. We could already guess that if there do exist solutions, there will be infinitely many. If not, then we may not even have a single solution. So to see that, we basically first again define my matrix made out of the three rows as well as my column vector B. Next, I define my augmented matrix. Now I calculate my row reduced echelon form for this augmented matrix. And here we run into a problem. You can see that there are two pivots, 1 and 1, but the third row is basically 0. So we can write down third row is basically made all out of zeros. In however, the RHS stays non-zero. This is a problem. This basically because you cannot have 0 into some vector equaling 1. So this basically tells us that this system of equations is inconsistent and does not have a single solution. And you can see how this system of equations, the third equation is being obtained. You can just subtract the first equation from the second equation. So 1 minus 2 is minus 1, 2 minus 3 is minus 1, 2 minus 9 is minus 7, minus 3 minus minus 4 is plus 1. And if you do 1 minus 2, you should end up with minus 1 here. But we have plus 1 here. If I change this, this is what I get. So this becomes consistent. And then you have infinitely many solutions for these two equations. So for the provided example, we do not have a single solution. Next, we want to solve a system of equations using Cramer's rule. In Cramer's rule, if you remember, so it's a 3 by 3, three equations in three unknowns, and solution may exist. In Cramer's rule, what we essentially do is whichever variable you want to calculate, right? Suppose we want to calculate the value for A. What we do is we place this right hand side into the column corresponding to the variable of interest. This creates a different matrix whose determinant we evaluate, and then we scale that determinant value with the determinant of this original coefficient matrix. I think it will become clearer in the code. So I'll first define my coefficient matrix A and my right hand side vector B. From this, I'll be again looking at the augmented matrix, sorry, row reduced echelon form once to verify our solution. So I'm augmenting B to matrix A and calculating row reduced echelon form. So this is what it looks like. So it seems that my values of A, B, and C would be 509.5 minus 417.5 minus 567.5. Yeah. If we use Cramer's rule, we have to calculate determinant of the coefficient matrix first. So that is assigned as D. Then we create a different matrix which has the RHS or the vector B. So 24 minus 11 minus 20 placed in the column corresponding to whichever. So like placed in the first column because we want to calculate the first variable. So that this is how we define the matrix dx, and then we calculate its determinant. So this becomes the matrix corresponding to A and its determinant. Similarly, I define a matrix corresponding to B, second column, and its determinant. Also, I do the same thing for C, third column, and its determinant. And then I can calculate my answer variable values from Cramer's rule as dx by d, dy by d, and dz by d respectively. So the answers are 509.5 minus 417.5 and minus 577.5, which are consistent with what we obtained from our row reduced echelon form. Okay, so this is a demonstration of Cramer's rule. Any doubts till now, or is it all smooth sailing so far? Okay, the final set of problems that we have are on vector spaces. So like the final part of the week. Suppose In this example, we are given that suppose the vector space V is equal to Q6, so which is basically a six-dimensional vector made out of rational numbers, and we have been given two sets of vectors b1 and b2 respectively. We are asked to calculate the linear span of set b1 and set b2 and assign them as w1 and w2, and then calculate the basis for subsets w1 plus w2 and w1 intersection w2. So first let us define vector space V, six-dimensional rational vector. So Q6 defined as Q raised to 6. Next, define B1 and W1. So B1 is nothing but B1 is nothing but made out of vectors belonging to real numbers. So they have been initialized as follows, and from that we define W1 to be the linear span of vectors belonging to set B1. If I do show W1, I get it as a row span in row span among rational numbers. So basically all these three, we get three independent rows from which we with which we can play around and from which we can construct our vector, uh, vector space W1. Same thing follows for the space W2. Again we define four vectors, calculate the span based on these four vectors. Each of these vectors has to be, we have to specify that they belong to Q2, because and if I do now W2, I get a row span that looks like this. Alright, so this is what we get. So all these four rows are independent. Now if I want to look at the uh, addition set of W1 and W2, I define that as WA, and if I do show WA, this is what I get. So it seems that W1 W1 has three independent rows, so it can have basically three dimensions. W2 has four, but the addition has five. We know a formula where dimension of W1 plus W2 is basically dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. So since this is 5 and the above two are 3 and 4 respectively, we expect the intersection to have dimension 2. And if I do that, W1 intersection W2 as WB, I can see that it's a row span of two rows, which basically confirms our formula. Okay, so any entry in say the intersection between W1 and W2 would be say of the whole A into the first row plus B into second row. So you can play around with it to find say any possible vector in W2. Okay, I think this was sorry, excuse me. Next example that we have is we want to write a basis of P3 of R, whose all elements are of degree 3. So P3 of R basically means a polynomial space. So any equation that is of the form ax cubed plus bx squared plus cx plus d belongs to P3 of R, where x, a, b, c, and d also belong to the real numbers. Here we are told that we can write our own random base or P3 of R, and from that we use it to calculate coordinates of this particular equation 1 plus ax 1 plus x plus x squared plus x cubed. So to do that, we go along this route. We define variable x, four different functions f1, f2, f3, f4, which are not linearly related. You can see that 1 plus x, 1 minus 2x, 1 plus 3x square, and 1 minus 4x cube. Right. And now we want to check if f1, f2, f3, f4 really form a basis. To do that, what do? We basically write down any random polynomial using these four bases. So a1, f1 plus a2, f2 plus a3, f3 plus a4, f4. And then we collect all the terms corresponding to x. So this is how it looks like. Right, so you have something like minus 64 a4 x cube plus 9a3 plus 48a4 and so on. So this collects those terms. Next, we want to see when if this equation, if we want to see if there exists solution a1, a2, a3, a4, provided that all the four coefficients go to 0. So why are we interested in doing so is because if uh, if the polynomial goes to 0, a1, f1 plus a2, f2 plus a3, f3 plus a4, f4, then what do we have is this is complicated. What do we have is if the linear combination a1, f1 plus a2, f2 plus a3, f3 plus a4, f4 goes to 0, provided a1, a2, a3 and a4 are all 0 at the same time, that basically means that f1, f2, f3, f4 are in fact linearly independent. So if we solve this equation, which is basically running all the coefficients 0, we get that the only possible way we could do so is if all the AIs also go to 0, which means f1, f2, f3, f4 are integer bases. Now that this is clear, we have chosen a correct basis. We define the function f of x, and then what do is for our random polynomial p defined as a1, f1 plus a2, f2, and so on and so forth, we compare the coefficients of p with coefficients of f. So from that we can expect straight away minus 64a4 to be equal to 1, which would be a4 equals minus 1 by 64. Similarly, coefficient of x square should be 1, coefficient of x should be 1, and the constant term is also 1, a1 plus a2 plus a3 plus a4. Once I solve these four coefficients and obtain the value of a1, a2, a3, a4 in the form of dictionary, I just print out the values. So as I mentioned, we expect a4 to be minus 164, which is what? 1 by 64, which is what we are also seeing here. Next, these are basically coefficients of the basis itself. And if I multiply, say, a1 into f1 plus a2 into f2 plus a3 into f3 plus a4 into f4 and expand it, I essentially end up with my original f of x, which was x cubed plus x squared plus x plus 1. Okay, so right, so I hope this problem is clear. Random polynomial, random basis, calculating coefficients, and so on and so forth. So next problem that we have is we have been asked now to define two random bases b1 and b2 for q raised to 4, and we want to find coordinates of the same of a given vector with respect to both the bases. And then we also wish to calculate the matrix for change of basis that relates coordinates of V with respect to bases V1 and V2. So V is QQ raised to 4. Uh, right. So if I do show V, that is essentially Q raised to 4. So sorry. Uh, right. So we have defined the vector space V, which is Q raised to 4. Next, we want to define two bases B1 and B2. For that, we define four vectors each for the basis set B1. Those are B11, B12, B13, and B14. These have been chosen at random, and the only the restriction here is that the vector must belong to rational field QQ. Once this B1 is there, what we do is we want to see if uh, we want to see what is the span of B1. We also want to see if B1 is in if the components of B1 are indeed linearly independent. To do so, this is what we get. So the span of B1 is, as you can see, it turns out to be a identity matrix 4 by 4. So any vector A, if any vector in V, which is say of the form A, B, C, D, can be written as A into first row plus B into second row plus C into third row and so on and so forth. So we can write any vector in V using the basis B. Same thing I do for basis B2. Again, same condition where we want to check the span and we want to check linear independence. For the chosen vector B2, it does turn out that we again have linear independence. Okay. Now, what we want to do is suppose we define a random vector V belonging to our capital V vector space. Now we want to calculate what is what are the coordinates of this vector V using basis B1. To do so, we first define a subspace in V using the basis B1. Next, we calculate coordinates of the small vector V using in the subspace W1. So that is D1, and I show the vector of D1. This is how it looks like. Okay. If I so like this is the inbuilt method to do so. If I want to calculate how uh, how the coordinates look like manually, what I could do is I could first start by writing the column matrix for vector for sorry for the basis B1. Next to that B1 matrix, I am augmenting my vector V, and I am calculating the row reduced echelon form. So you can see that. Sorry. Okay. So what all is happening here? Once we define this matrix M, this is the first vector in B1. This is the second vector in B1, third vector in B1, and fourth vector in B1. Each of these are multiplied by some scalar, say A, B, A times column 1 plus B times column 2 plus C times column 3 plus D times column 4 equaling my right hand side column, which is vector V. Right. Now, to calculate what those values are, we basically do row reduced echelon form from which we obtain the solutions in this form. So these four values are basically my coordinates of vector v. If of vector v in basis b1. Again, same thing I do for basis b2. So if I create another column matrix, to that I augment my uh, vector v, and I run this. What do I see? This is my all these four columns basically are my basis b2. This is the vector I want to represent, and if I do row reduced echelon form, I get the scalars to be multiplied to all the four rows as given here. So 227, 2728 by 355, and so on and so forth. Now comes the slightly tricky part. We want to see how how we go from say how we transform basis. So we have vector v in basis b1. To this we multiply a matrix which is basis transformation from b1 to b2. That gives us vector v in matrix b in basis b2. And this matrix is defined by writing the columns of W2, so writing a column matrix. So each of which entry, so it has four entries, so 1, 2, 3, 4 columns, and each of those columns are basically columns of vectors belonging to basis b1, which are b11, b12, b13, b14. All those four vectors return in coordinates form of W2, which is nothing but the subspace defined for basis B2. So this basically means is each of these four vectors 1, 2, 3, and 4, each of these four columns belong to basis B1, and now we calculate coordinate of say the first column with respect to like the basis B2. So that will give us some four values like this, and so on and so forth. So that will create a 4 by 4 matrix. This looks like this. So what does this mean 1000? This means that the first vector b11 is 1 times b21 plus 0 times b22 plus 0 times b23 plus 0 times b24. You can see that once you look at b11, which is nothing but 2 minus 3, 2 minus 1 3 1, which is same as b21. So I purposefully put b11 and b21 as same so that it's easier to grasp what is happening here. Okay, now if I get the coordinates, this is d1 is the coordinate with respect to basis b1. This is d2, which is the coordinate of vector v with respect to basis b2. To verify our relation, we'll be multiplying our basis transformation matrix with our vector d1. So coordinates this, and that should ideally give us d2. Right? So is this equal to d2 dot vector of d2 dot n? This is what we want to see. Right. So our method is indeed correct for basis transformation, and this is what we obtain. Okay. Bit of an involved problem. If you have any doubts, you can ask here now. I understand that there are a lot of things happening in this question. Basis transformation is something that I have felt that a lot of people have some confusion because it's hard to define, like say one reference frame and then another, and how do you go from between the two reference frames. Hopefully the key logic is clear that we'll be basically looking at uh, basis B1, all those four columns, through the lens of basis B2 and calculating their respective coordinates. Okay, if I want to see how this works manually, what I could do is I could say for B2, instead of adding B, we say check B1. So B11 is 1000. I do B12, my augmented matrix, my row reduced echelon form is these four values. So these four values are same as this column here. If I do B13, and if I do same as the third column above, if I do B14, same as the fourth column up. Right, so coordinates of basis B1 vectors with respect to basis B2. If another thing is that I think this you can expect is that suppose I want to take coordinate of one of the vectors, say B22 with respect to basis B2, you can like if you think about it, you already know that this has to be uh, independent of all the columns except the column that it represents. So like second column of B2, this is what we get, 0, 1. Okay, so that completes the problem of coordinate transfer. Hopefully it's clear. If not, you can ask any doubts on that now. Okay, now we move on to the next and final problem for the day. We have been asked to calculate a basis for a set of vectors given here. So we have been given five vectors. Sorry, we have been given five vectors, each of them having four entries. So five four-dimensional vectors. From this, one thing that you already know is that if we have more than like the if we have more number of vectors than the dimension of the space, we expect it to be uh, linearly dependent. So, so yeah, right. So we have to find the basis for this set, and to do so, we have been we have five vectors L1 to L5 belonging to QQ and having four entries each defined above. Now I define from this five vectors L1 to L5, I define the set L containing L1, 2, 3, 4, and 5. Now if I do, next thing I'll do is I define the vector space V, which is four-dimensional rational numbers, which is made up of four rational numbers. It is q raised to 4. Next I define the subspace W, which basically is V dot span of L. So subspace W using span of L. So what I get. So this creates a basis. So what do we see is that even though V is four-dimensional, W has like three rows, so it only has three dimensions. And to check if this is indeed correct, what we are doing is for each of the entries in L, we are printing whether that entry indeed belongs to subspace V as well as subspace W. So we expect it to be true, but just wanted to show how it works. So even though we have five vectors, the dimension of the subspace that comes out from linearly spanning those vectors is 3, and it's a subspace of the vector space Q raised to 4. Okay, so this covers up the problems that I had for this for today's live session. If we have some time left, so if you have any other doubts related to what we have studied so far, you can ask them now. I think then we'll close this session. It seems that all the examples that we have covered are understood. Okay then. Yeah. Thank you for watching this, attending this class, or watching this on YouTube. I'll see you again in the next one.